Yeah, okay, so, what's this all about? Well, I probably don't need to define a RAAG, do I? Okay, so, gamma is a simple graph. Then A gamma is the associated RAAG. So you just say the vertices are the generators of the group, and the relations are, there's a relation that two of them commute, but there's an edge between them. Right, so RAAGs have lots of subgroups. And in general, they have lots of interesting subgroups, like three-manifold groups. Virtually all hyperbolic three-manifold groups are subgroups of RAAGs, or I'm not sure that I got the virtually in the right place, but anyway. They have lots of interesting subgroups. Everybody is probably fairly convinced of that. But actually, in rare cases, every finitely generated subgroup of a RAAG is actually a RAAG itself. So this is proved by Carl Droms. If gamma does not contain this graph, which is called L3, or this graph, which is called C4, as a full subgraph, yeah, for a while, until it gets
What's full?
Yes, I was just about to say that. Full subgraph means if you've got vertices in your subgraph, then every edge that uses those vertices is also in the subgraph. So, for instance, although this has a C4 in it, it's not a full subgraph because it has an extra edge. Okay. If gamma does not contain that or that as a full subgraph, then every finitely generated subgroup of A gamma is a RAAG. Okay, so the question becomes interesting for graphs that do contain these things. Right, so I want to explain next why I'm interested in RAAG subgroups of RAAGs. I mean, in cases other than this. So I'm actually sort of interested in automorphism groups of RAAGs. In particular, outer automorphism groups. Of course, your two examples of RAAGs are free groups and free abelian groups. They have interesting automorphism groups. But so this is out of Fn, this is GLNZ, the automorphism groups. They're interesting groups. They share a lot of things in common, but they also are fundamentally different in lots of different ways. For instance, Formanek and Procese showed that out of Fn has no faithful linear representations if n is at least 3. N equals 2 out of F2 is SL2Z, and it certainly does. So this is obviously different from GLNZ. Okay, so there's a sort of a fundamental dichotomy there. A couple more of other facts about out of Fn. Actually, Mark Color and I proved a long time ago that any action out of Fn on a tree has a global fixed point right. Yeah, this is also if n is bigger than or equal to 3. So it doesn't have any faithful representations, can act on a tree.
What about what kind of subgroups still have no global fixed points?
Sorry, well
Subgroups.
that's not clear.
Yeah.
Right. That's we'll get to that in a minute. Any action about Fn has a global fixed point, so that implies in particular that out of Fn doesn't have t. Yeah. Sorry. It does not apply that. Never mind. Right. However, right, the next statement was about a finite index subgroup. Where are you? Lubotzky. Actually,
So these are signature trees or
any R trees.
are trees?
Lubotzky, actually this example was shown to me by Casson about 20 years ago. So I'm not sure exactly who to attribute it to. But Lubotzky at least showed that there's a finite index subgroup out of F3 that does act on a tree. So now I can say, so out of F3 does not have T. And the question is still open for n bigger than or equal to 3. I did this wrong, didn't I? Question, does Fn n bigger than 3 have T? So the reason the reason this finite index subgroup acts on a tree is that this finite index subgroup, it maps onto SL2Z, which acts on a tree. So therefore, okay, so I want to give you the idea of this proof, which will explain something about why I'm interested in the original question. So here's the idea of the proof of Lubotzky's theorem. So we're going to look at an index 2 subgroup of the free group. Yeah. Index 2. So it's going to correspond to a double cover of the rows. C, A, B, A, B. So I one of this is equal to K. And what we're going to look at, so this is the kernel of the map that sends A to 0, the map from F to F3 to Z mod 2, that sends A to 0, B to 0, and C to 1. Okay, so here we have a subgroup of this free group, and we're going to look at automorphisms of F3 that send K to itself. Since there are only finitely many subgroups of index 2, this is a finite index subgroup of out of Fn. And, right, notice that the fundamental group up here has rank 5, and the det group is Z squared. Z mod 2. Let's call this R tilde. And it's easy to check. Right. It acts on R tilde, therefore, on the first homology of R tilde, which is isomorphic to Z to the 5th. And automorphisms of F3 that preserve K lift to automorphisms of, well, they said they're automorphisms of K. So elements of aught of F3K also act on the homology of R tilde. And it's easy actually in this case to check that these actions can use. So in other words, this group, since they commute, this action preserves the eigenspaces of the Z2 action. Okay, so the homology of this guy is 5-dimensional, and you can check that there's a Z2 action, so there's exactly 2 eigenvalues, +1 and -1. One of those eigenspaces has dimension 2 and one has dimension 3. Which one? I can't remember. The -1 eigenspace has dimension 2, and so you get a map from this isomorphism group to the eigenspace, which is isomorphic to Z squared, automorphisms of Z squared. And it turns out this map is surjective, and then you're done. So you have a finite index subgroup, it maps to auto Z squared, and it turns out that that's surjective. So that's just, I mean, that's pretty much the whole proof. It's really neat. I really like that. Grunewald and Lubotzky wrote a paper in which they vastly generalized this example. What were they looking for? They were looking for representations of higher rank automorphism groups of dimension 2. They're looking for eigenspaces of dimension 2. They didn't find any, but they found lots and lots of interesting representations of, oh, I should say this also, this map, I'm in the automorphism group here, but you also get an action on the outer automorphism group. So, Grunewald and Lubotzky generalized this. So whenever you have a finite index subgroup of a free group, a Q, given a projection, look at K, paternal, look at this guy, and then look at automorphisms of Fn, reserve K, that's finite index in aut of Fn. And I also needed the fact that the action of the subgroup commutes with the action with the deck transformations, which is automatic in this case, but isn't always automatic. So we have to go to a further finite index subgroup on G Fn K with automorphisms commuting with deck transformations on H1 of the cover. Okay, so, and then,
G stands for the
Uh,
group.
G stands for Q. Qx by deck transformations, right? There it was
Yeah, yeah.
Z2. Right, so X by, so this guy is finite index in aut of Fn, and so the fact that they commute with the deck transformations implies they preserve the eigenspaces. And you can look for small eigenspaces. Unfortunately, the smallest eigenspaces they managed to find have dimension n minus 1. So if n is bigger than 3, n minus 1 is bigger than 2. So we don't get actions on trees, but we get lots of interesting representations. I don't want to, there are lots of reasons these are interesting, but I want to get back to the subject of my talk at some point. Right. So I started off talking about RAAGs, and I said I was interested in automorphism groups of RAAGs. So the question is, what can you say, or can you find analogous interesting representations of A gamma? And maybe, right. So I should say that, yeah, all of the Grunewald and Lubotzky representations kind of show up in automorphisms of A gamma in the following way. I don't like this system. You can't see what I wrote. There must be a better way to do it. So here's some facts. So the answer, of course, depends on on the structure of gamma. So let me introduce some, let's start talking about what gamma looks like. Some notation, V is a vertex of gamma, then the link of V is a set of vertices adjacent to V, or the subgraph. And by vertices adjacent to V. So here's V, here's all the vertices that might be adjacent. Some of them might be joined by edges. The link of V is the full subgraph spanned by that. And the star of V is the full graph spanned by the link of V and V. So stars are purple. So you take this and join it with V, that's the whole star. Of course, there's more to the graph goes off here. Okay, so that's the link in the star. What else do I need to say? There's a kind of a partial ordering on vertices. Say V is less than or equal to W if the link of V is contained in the link of W, in the star of W. So there's basically two ways that can happen. Here's V, here's its link. Then that has to be in the star of W. Well, if V and W are not connected, then W looks like that. If V and W are connected, then it looks like that. In both of those cases, V is less than or equal to W in this ordering. So it's not a partial ordering because V can be less than or equal to W and W can be less than or equal to V if they have the same length or the same star. So say V is equivalent to W if V if that's true, and then this curly guy induces an actual partial order on equivalence classes. That's standard terminology when you're talking about right-angled arc groups. So these guys are equivalent. If they're not joined up by an edge, it's true if everything is equivalent to it. They're not joined by an edge. It's called a non-abelian equivalence class. I'm going through this kind of quickly because I think that probably most people have seen this before. Is this true? No. Okay.
Another question.
Yeah.
What if there's, say, three vertices, V, W, and X, and V and W are connected and X
That
isn't?
doesn't happen.
Never happens.
It's a lemma.
Okay, so
Exercise.
it's either all connected or all.
It's either all connected or all not connected.
So what does it mean, non-abelian or abelian?
So an equivalence class means the guys either have the same link or the same star. They're equivalent if they have the same link or the same star. So these guys are equivalent, and this is a non-abelian equivalence class because they don't commute. And it turns out, and to answer Rich's question, if I had a third guy, either all three of those equivalent to these guys, either none of them commute or they all commute. So that there's non-abelian equivalence classes and abelian equivalence classes. And there are some propositions to Ruth Charney and myself. If you're looking at outer automorphism groups, then their natural projections that contains a certain finite index subgroup, and there are homomorphisms out 0 of a gamma to out of a gamma minus v, and it's called restriction. And, no, sorry, this is called exclusion. And out 0 a gamma to out of a v, this is called restriction. If v is maximal, so this comes from understanding the generators for, you just check it's true on all the generators of this subgroup out 0, and it's true. Right. So if v was maximal, then this is a finite index subgroup of out of a gamma. It maps onto out of a v. If v is a non-abelian equivalence class, this is out of f cardinality of equivalence class. And now we can pass to a further finite index subgroup and get all these Grunewald and Lubotzky representations. So so you just get that from looking at this. If v is maximal, if v is not maximal, well, then what do? You have a map from this, you just throw out anything bigger than v, one at a time, and you get out of a gamma onto out of a gamma minus. If w is bigger than v, you get an exclusion map from out of a gamma to out of gamma minus w. And if there's still something bigger than v, you throw that out too, and you keep throwing that out until finally v is maximal, and you compose it with this, so you get a map. I have to say that maybe it's about time to start turning off the.
These morphisms are onto what's our imaging?
Yes, they all are onto. This is onto out of 0, and this is actually onto. So I gave talks about a related thing for a while, and I didn't realize that I get a homomorphism even whether v is maximal or not. It follows by just throwing out bigger ones until you make v maximal. And then Girardot and Sales noticed that there was a homomorphism, but they didn't realize it followed from earlier stuff.
So in your gamma minus bracket v, you throw out all the vertices of
Right.
v and everything connected to them.
I just throw out
Everything, all the edges.
in the whole equivalence class.
Sorry, I don't understand why is that out of the free group? I mean, when you restrict.
So I'm if v is maximal and non-abelian. So if B is maximal, sorry. You're absolutely right, sorry, this has nothing to do with abelian or non-abelian, or
FGL.
GL and Z. Okay. So in particular, if there's an equivalence class of size 2, for instance, I get an action on a tree from this. If there's an abelian equivalence class of size 2, or non-abelian equivalence class of size 2, I get an action on a tree. If there's a non-abelian class, equivalence class of size 3, I get an action on the tree. So in either case, if there's abelian classes of sizes 2 or non-abelian equivalence classes of size 3, I get the guy doesn't have property T. Compose each of these with one last times the B to get out 0 A gamma onto out of A sub V. Okay, so we get all of Grunewald and Lubotzky's representations somehow. If we have equivalence classes of the appropriate size, non-abelian equivalence classes of the appropriate size. But the question is, what if we don't? Or, actually that's not the question. The real question is, can we go back to the original construction of Grunewald and Lubotzky using a little bit of covering space theory to find other interesting RAAG subgroups and attempt to use them to find other interesting representations of out of A0. So we're back to where I started. So my real question is, right. I wanted to say one more thing about the Grunewald and Lubotzky thing. What makes their stuff work is, they use an inductive arguments, and they get to use inductive arguments because when they look at the kernels of their homomorphisms from a free group to a finite group, those are always free groups, right? So we would also like to use similar inductive type arguments, but it's not true that the kernel of a homomorphism, well, this was a question we had actually. If you have a homomorphism from a RAAG to a finite group, is the kernel always a RAAG? The answer is no. And then we started asking, which subgroups, which normal finite index subgroups of RAAGs are RAAGs. So we want to imitate Grunewald and Lubotzky construction on RAAGs to look for interesting representations. But we need to know, question, when is the kernel of a map from A gamma to Q finite RAAG. So that was the question. So now I've finished my introduction. So we know by Drom's that this is only an interesting, it's always a RAAG unless gamma, in certain restricted cases it's always a RAAG, but most of the time could or could not be a RAAG. So here's what we came up with. So we have this this equivalence relation on vertices. So it turns out you can actually find a subgraph gamma whose vertices are the equivalence classes. And their edges, if the equivalence classes commute. And in fact, you can embed gamma naught in gamma by just picking appropriate elements of the equivalence class. And this isn't part of the definition, this is a fact. Which is in Carney. Okay, so I'm going to use this gamma naught to define an invariant of pi. Pi is a homomorphism which is finite. So, yeah?
I guess this is probably the same question. If you have one equivalence class and another, and there's some edge joining one thing and one and the other, then everything's connected? Everything in one is connected to the other?
No, if the equivalence class is, no, everything in the same equivalence class is either joined.
Right, so what does it mean for equivalence classes to commute?
Maybe, let's see, how do I say this? Well, it means everything in one equivalence class commutes with everything in the other equivalence class.
Okay, so they're all joined.
Yeah, they're all joined.
Okay.
That's right. If V is joined to W, then everything that's equivalent to V is also joined to W. And everything that's
That's right.
equivalent to W is also joined to everything that's equivalent to V.
Yeah, yeah.
Yeah, I guess it's the same question, I'm sorry. So we got a map to a finite quotient, kernel pi. And I have this graph embedded in gamma, and I want to define a number d pi to be the maximum of the distance in gamma naught between the equivalence class of V and the equivalence class of W, where V and W are not in the kernel. So what do I mean? I've got a graph, and I've got all these vertices in my graph, and I'm looking at, this graph doesn't have any equivalent vertices, but this pi is determined by what it does to the generators. Some of them get mapped trivially and some of them don't, okay? So I'm looking at the ones that don't get mapped trivially and looking at the two that are the farthest apart. And that's my number D associated to pi. So that's my number. So for example, if D equals 0, that means there's some equivalence class, a bunch of vertices. They all have the same length. Maybe I should draw them like this. And then there's the rest of the graph. And everything gets mapped to 0. Except for some of these guys. These are the only things that could have a non-trivial image in my group. So I claim, in this case, the kernel of pi is a RAAG. why is that? Well, yeah, there's these things called Salvetti complexes. So this has a loop for every vertex, and if I have a clique, a set of vertices that commute, I glue in a torus. Are there people that haven't seen Salvetti complexes
We have seen, but we don't remember.
before? Okay. Okay, let me draw the picture over here. I have V1, V2, and V3 are correspond to loops. There's a loop for every generator. V1 commutes with A, so there's a V1A torus, there's a V1B torus, there's a V2A torus, there's a V2B torus, a V3A torus, a V3B torus. In other words, this whole thing is a product with a torus. Yeah, there's a torus. Sorry, it's not a torus. It's I haven't said whether A and B commute. There's a link down here. Link of V, which is the same as the link of any VI. And what I have down here, there's a Salvetti for this link, and everything in this Salvetti for this link has a product with every loop up here. So actually I have, inside my Salvetti, I have a copy of this guy crossed with the Salvetti for the link of the, yeah. If I had 3 generators that commuted, I would have, I would glue in a 3 torus. Because I have, yeah, these are 3 sides of 3 torus. What does my Salvetti look like here? This is relevant to this claim. It's got this piece, which is a Salvetti of this, and it's got a piece, which is the Salvetti of gamma 0, and they're joined along the Salvetti for this link. Better pictures. I'm sorry, and Jerry, I was supposed to have better pictures. Let me just draw the case. Well, let me do this. Is everybody, is this picture clear or not? Should I try to explain this better? People don't look happy.
Commissioner, what was gamma 0?
Gamma 0 is
Just everything.
gamma minus
Everything but the V's.
everything but the V's. So, I mean, on the level of, what's the one skeleton of this thing is just a loop for every vertex. Lots of loops. 3 of these loops are in V. Let's just make one loop in V. Supposing that's V. Some of the loops commute with V. So every loop that commutes with V gives me a little torus. So if I have 2 loops commuting with V, I have a little figure 8 crossed with the torus. Or maybe these commute and there's a 2 torus and that's crossed with the circle. But in any case, I get whatever I get. In this case, these 3 guys don't commute. There's no commuting relations. So the 3 edges here don't commute with each other. So that's just, but they do commute with other stuff, which gives me this product, and they commute exactly with stuff that's in the link. So that gives me a product of this little rows with this link. And then I get all this other stuff. These are the vertices in gamma naught. And if this was my equivalence class up here, stuff down here is connected to only stuff in the link of V. It's never connected to V. So the only way it's joined to the rest of the whole Salvetti is just the Salvetti for this part joined with the Salvetti this part, and they intersect along the Salvetti that part. It's important to understand this picture if you're going to understand what I say next.
So here I have a question.
Mhm.
So if you look at the subvalue of the link of V, it's a subset here where it's like the vertex cross.
In my case here, the Salvetti was the link was just 2 points.
No, I mean you want to see the subvalue of the link of V as a subset of the bouquet of 3 circles cross the subvalue of the link of. You're joining these two things up.
Right.
It's the central vertex cross.
The central vertex.
I'm just saying this.
There's only one vertex in the
Right.
whole Salvetti.
It's that cross that it's
Right.
identified with.
You have a wedge of circles
Yeah.
and you glue on some toroid to them. And what you end up with is a locally cat
Sure.
zero space, which is K by 1 for the group. And this is what it looks like. Right. So, the claim is that if all these guys get sent to 0 but some of these don't, then the map from A gamma to Q factors through A and B. All of the vertices that aren't in B get sent to 0, and this is a free group. In this case. And that's exactly this free group here. So the kernel of this map is another free group, corresponds to some graph. And this graph has Q vertices. Index Q. This graph has Q vertices. When I look at the cover corresponding to this group, the only thing I'm unfolding is this guy. All these other loops, they don't get unfolded. They're just still simple loops upstairs. Nothing happened because they got sent trivially. So the only thing that gets unwound upstairs is some of these loops. And so some of these loops get unwound to give me a graph. I've got Q vertices. And so this cover, S tilde, this is S gamma, cover, which fortunately I'm drawing down here instead of up there. What does that look like? It's just this crossed with a bunch of copies, Q copies of the link of V. So every one of these points gets its own, well, the whole thing is crossed, sorry. The whole thing is just crossed with the link of V. You get that? Where I need a Q is, I've got now Q copies S gamma naught because I have a subgroup of index Q. And how do I visualize that? Well, there's one at every vertex. So let's suppose the link of V is just a single point. Then I can draw a picture. Okay, so then what is this? This is just this crossed with the circle. I don't know if I can draw it or not. But So then this whole thing is this crossed with a circle. And at each of these vertices, I have a little copy of, so the whole thing is this gamma crossed with a circle and a little S gamma not hanging off at each edge. Okay, that's what the cover of this thing looks like. Now it's obvious what to do. So what am I trying? I claim that the kernel of pi is a RAAG. This guy has fundamental group, the kernel of pi. That's how I made it. It's the cover corresponding to pi. So all I have to do is show that this thing is actually homotopy equivalent to a Salvetti. Okay, so in other words, it's just got one vertex, a bunch of loops, and some tori. But then it's obvious how to do that in this picture. You just take a maximal tree in your graph that corresponds to some little hyperplanes. The cross sections are S sub length of V's. And you can collapse all those hyperplanes independently. Since all these things are hanging off independently, nothing happens. And this is homotopy equivalent to just a rose. In this case, well, it started off with 3 petals and the cover just had 3 petals. That's not so realistic, is it? The cover has a higher rank. Okay. So, in fact, it's got rank Q minus N, well, you can figure out the rank from the other characteristic. So that's homotopy equivalent to this, crossed with Salvetti for the link. Yeah. Union Q copies over one copy of the Salvetti for the link. Q times the Salvetti for gamma minus gamma. So I feel like I'm not being particularly clear, but I claim this is really obvious if you think about the Salvetti and what this map does. The only thing it does is opens up this rose into a graph on this whole Salvetti picture. And so so then if you collapse the maximal tree in this graph, you're going to get something that's again a Salvetti. All you have is tori. You haven't introduced any strange identifications. You just have some tori and one vertex, a wedge of circles is a one skeleton and a bunch of tori attached. So therefore it's a RAAG. Yeah. That was D equals 0. Let me tell you what the answer is if D equals 1. And D equals 1. And let's assume that gamma is a tree. Or at least gamma. Actually, all you need is that gamma naught is a tree. But let's just assume gamma is a tree, so we don't have, yeah. Okay, so what does this mean? The maximal distance between guys that map non-trivially is 1. So that means there's 2 vertices, V and W, that are adjacent that could map non-trivially. We may as well assume they do. Pi of V is 1, pi of W isn't 1. In this case, there's I'll tell you the answer is proposition. If you look at the subgroup generated by pi of V, and it intersects the subgroup generated by pi of W, trivially, then kernel of pi, let's see, trivially, that means that. Yeah, then the kernel of pi is a RAAG. Yeah, of course. If pi of v intersect pi of w is not trivial, and then if v or w is a leaf, implies the kernel of pi is a RAAG. If neither, otherwise, kernel of pi is not a RAAG. So I guess I misjudged my time as usual. I wanted to at least show you an example of how you show that something's not a RAAG. In this case, this goes back to a theorem of Drom's. If gamma is a tree, so I'm just going to tell you some stuff here. If gamma is a tree, then Drom's shows that A gamma is in fact coherent. Every finitely generated subgroup is finitely presented. And in fact, if gamma is a tree, Drom's also shows that actually this is a three-manifold group. And actually, Cameron showed that a more general theorem for general Artin groups, that if there's a graph you can associate with a general Artin group, you can put numbers on the edges instead, and if you get a tree, then you get a three-manifold group. And that's almost the only cases you get a three-manifold group, with three torus. Right, so the point is anyway that A gamma is coherent. So what if we had something like this, pi of v and pi of w are not equal to 1, and in fact they intersect non-trivially, then I claim that, actually it's not this. Okay, I'm sorry, coherence doesn't come in here. I shouldn't try to do the rest of the talk in 5 minutes. This is this case. D is bigger than 3. Where coherence is important. So these guys are in the kernel and those guys aren't. And what happens is you analyze centralizers. So, so V tilde corresponds to, yeah. So some power of V is in K. And some power of W is in K. And then there's, right. I can't explain this. You got these guys that are in the kernel. What you're going to do is show that if this kernel was a RAAG, then in fact these guys would have to be generators of the RAAG. And you do that by studying centralizers. And then you use this chain from V to W to construct a loop in the generating graph. It's got V to the A and WB. No, sorry, it has these guys, A1 and K. A1 and AK in it somewhere, and you get a bunch of things. The graph has a long generating loop. And that loop is embedded. And then Drums tells you that the right-angled arc group associated to that graph is not coherent. I feel like I'm not being very coherent right now either, but this is not coherent. But of course, if you have a subgroup of a coherent group, it has to be coherent. And I'll stop there.